Hey everyone. In this video lesson, we're going to be taking a look at electromagnetic induction. So if you remember from the last couple of videos, we looked at how Hans Ørsted discovered that when you send a current through a wire, okay, it generates a magnetic field, like in the picture in front of you. And we looked at how using the right-hand rules, once that current gets going, we can use the right-hand rules to determine where the which direction the magnetic field is acting in, or the B field, as we sometimes call it, because it uses a symbol B to represent it. That's the picture through a single wire. We also looked at how a solenoid works. So if we take all of the wires and loop the wire repeatedly, it'll create a magnetic field set with the north end at one opening of the solenoid and the south end at the other end of the solenoid. You can see the picture to the right shows the magnetic field in that situation, wires going in and out on top. And we have the north, and it's compounded largely inside the tube. Now, Faraday, a few years later, he said, well, if we take a current and run a current through a wire and it generates a magnetic field, what would happen if we took a magnetic field and passed it through a wire that doesn't currently have a current through it? If a current can create a magnetic field, why can't a magnetic field create an electrical current? And that's exactly what he did. And this breakthrough led to the creation of motors and generators. All of our power plants essentially operate on this idea of electromagnetic induction. Okay, so a really huge breakthrough that let us create a lot of different new tools. Your wireless charging on your phones or other tools is through electromagnetic induction. Okay, so how it works. So here is a galvanometer. Okay, and a galvanometer is a little bit different from a voltmeter. So a galvanometer, it'll measure the change in current through a wire. Okay, so what's happening here is we have a coil. There's no battery hooked up to this or anything. It's just a coil of wire in a loop. And what happens when the person takes a magnet and moves the magnet through? We see the galvanometer. Here is the zero line on the galvanometer. When you move the magnet up through, okay, it starts to create a current. So we get a positive voltage. When you pull it the other way, so when you pull the magnet down through the loop of coil wire, it creates a negative voltage. Okay, so by moving the magnet in different directions, we actually create alternating currents. Now, if we switch the magnet end, so if we change to the south end on the top and do the same thing, we see it still creates a current, but with the south end, the current is just the opposite. If we move it up through, it goes a negative. If we pull it back down, it goes a positive. And lastly, what happens if we have a stationary magnet? So Faraday found that if you just leave the magnet sit in the middle, even though there is a magnetic field, if the magnetic field is not in motion, then no current is created. Okay, so if we stop moving the magnet or stop moving it, we could also move the wire up and down past the magnet to give the same effect. But if the motion stops, so does the current, which is why this is referred to as induction. It's an induced current, so it's only there as long as the motion is happening. So a changing magnetic field can produce a current as if there were a source of electromagnetic force, or EMF for short, or a voltage. So again, we call this induced EMF, and the current is an induced current. So this property of a change in magnetic field, so we move that magnetic field up and down, so the motion of it, we call this magnetic flux. So magnetic flux, with the symbol there, refers to the total magnetic field in a given area. Okay, or how many field lines. So we can look at a stationary magnet and we can just see, okay, how many field lines are gathered up in one particular place? How strong is that magnet in one spot? And that gives us the flux. Okay, so this symbol is equal to, I want to say the Greek letter iota, but I can't remember for sure. Wait, not iota, phi. The Greek letter phi is equal to B perpendicular times A. So B perpendicular is the component of the magnetic field that is perpendicular to the area surrounded by the conductor, and it's measured in Tesla, just like any magnetic field. If we're looking at a magnetic field, we're not going to study ones on angles here, but if we were, we would add in the cosine term to figure out the perpendicular component of that. A is the area in squared meter, and magnetic flux, that phi, is measured in what we call Webers, or WB for short. So Faraday's law of induction, so we need to figure out, okay, so we have our magnetic flux, but how much voltage can we actually get out of this? How much power can we generate? So the induced EMF, or the induced voltage that's observed in a coil, is given by N is equal to the change in magnetic flux over the change in time. So where N is the number of loops in the coil. Okay, so if we had a singular wire, that would just be 1. Okay, the negative side, so notice that there's a negative in front of here. Okay, so a way I like to remember this is that nature opposes change. Things, including people, we generally, don't like change. So this negative sign is to show us that the induced EMF is always going to be the opposite direction as the change in magnetic flux. So again, this is our flux change, and this is our time change. One of Faraday's original experiments you can see in the picture there. So we have a battery. Just let's think about this for a second. Attached to a wire which is coiled around this piece of iron. When you close the switch here, okay, what this does is create a current. The current goes through. That current generates a magnetic field, right? Because we really just have, in this little piece here, we really just have a solenoid, a bunch of groupings of coiled wires, creates a magnetic field. That magnetic field passes through this piece of iron. Okay, as the current keeps moving, the magnetic field keeps moving. And since the magnetic field is passing through down here, we have a moving magnetic field in this loop of wire, so it generates a current in this loop of wire at the bottom, and we'll see the galvanometer start to get a voltage. So Lenz's law says that an induced EMF always gives rise to a current whose magnetic field opposes the original change in flux. That's where that negative comes in again. So what this means, if we take a magnet, let's say we want to generate a current in this wire. If we take a magnet and we pass it through to the right with the south end facing toward the coil, okay, so the current's going to flow in such a way that it creates a magnetic field that opposes the magnet going through. So if we move, this is how we can figure out the direction of current. If we take this magnet and we move it through, it's going to oppose the motion of the magnet. So the magnetic field generated by the solenoid puts a south because it wants to repel that magnet back out. So we have a south to the left. These two ends repel each other. And the current within the solenoid, we can figure out the direction by using the second right-hand rule that we studied previously. Let's take a look at an example. So we have a 10 centimeter circular loop of wire is in a 0.5 Tesla magnetic field. It's removed from the field in 0.1 seconds. What is the average induced EMF? So you can imagine here is, okay, here's my loop of wire. And in that loop, we have a magnet that's being passed through, so we can just say the magnet has a north end here and a south end here. And the magnet is inside the loop, and we pull that magnet back out of the loop. Okay, so by doing that, so the magnet, we have its strength of the magnet, or its B field, is 0.50 Teslas. Okay, it's removed from the field in 0.1 seconds. So we're taking it, we're actively pulling the magnet out of the field. So we have our time is 0.10 seconds. And we know that the diameter of this loop, okay, which I'm going to change to meters, is 0.010 meters, which means our radius is half of that, so 0.050 meters. and there's just one loop in this case, so we have an n equal to 1 for the number of loops. So the first thing we need to do is figure out the change in flux. So when we pull that magnet out, how does that change? So our change in flux is equal to our final flux subtract our initial. Well, if we pull that magnet directly out, or if we oppositely, we could move the wire as well. If we move it out of the field, our final flux is going to be 0 because the wire is no longer in the magnetic field. And then this is subtract our magnetic field times our area. What is the area? That's a good question. Since we're dealing with a circular loop of wire, our area is going to be equal to pi r squared. So we can substitute that into our formula over here. We get negative 0.50 for our magnetic field times pi 0.050 squared, which gives us a change in flux of negative 3.9 times 10 to the negative 3 Webers. Okay, and lastly, we were asked to find the average induced EMF, which means we're looking for the voltage. So we have our change in flux. Now we just fill in our voltage formula. So voltage is equal to minus N times the change in flux over the change in time. Okay, our N in this case, again, is 1 because it's just one singular loop. We have our change in flux. Oh, I forgot my negative here in front. There we go. Times 10 to the negative 3 divided by 0.10 seconds. And that gives us 0.039 volts as an induced EMF. So if we were to continue to move it in this fashion in and out of the loop, we could create it would be an alternating, so it would go 0.039 and it would flip from positive to negative for average. But we could generate an alternating current by moving this magnet or moving a loop repeatedly over the magnet in the same fashion. We can also have the induced EMF in just a conducting wire. So this is going to kind of look at, so the idea of this is we're going to look at more or less what happens when we're changing the area. So imagine we have a conductor that's shaped like this U to the left here. Okay, so we have our width, and we take a conducting wire of length L. So here it is, here's our conducting wire, and we take this wire and we move it to the left. So what this is effectively doing is shrinking the area. So instead of changing the magnetic field, we're changing the amount of area that's the magnetic field is affecting. Okay, so we induce an EMF by changing the area. If we have just a wire, so we know our Lenz's law is we have the voltage is equal to minus N times the change in flux over the change in time, okay, which we can change to, so the number of loops is just going to be 1 times the change in flux is B times the area over our change in time. But area in our previous one we just looked at is just equal to the length of the wire times our change in width. So where are we moving that wire to over the change in time? What do we have here? We have a change in time, conveniently over a change in distance, and that gives us the equation BLV, so our change in distance over time, which is the magnetic field times the length of the wire times the velocity you're moving the wire through. Now this negative is just going to tell us the direction of the voltage, but we can kind of ignore this because we're just going to use the right-hand rule. So oftentimes I'll ignore the negative here and use the right-hand rule instead to figure out the direction. Okay, so if we have a wire flowing moving to the left here, so current must flow in a direction so that the force of the wire is to the right. Now remember, if the wire moves to the left, the force on the wire, because nature opposes changes, we're moving it to the left, so that means there's going to be a force trying to push it backwards to the right. Okay, so if we use the third right-hand rule, our palm must face to the right, right? Because our palm, coming out of our palm represents the force, so you face your palm to the right, fingers point into the page, and your thumb points down the page, which means that the current, okay, is in this direction, so down the wire. Now you may be asking, hold on, this wire isn't actually attached to anything. What's going on with the current? So what would actually happen here as we move the wire through is you would get a buildup of electrons. Remember, current represents positive motion, so you would get a buildup of electrons on this end of the wire, and it would create a potential difference between here, if we assume that's point A, and point B. So it would create a potential difference between those 2 points due to the movement of electrons through this rod. So let's take a look at one last example. So you have an 8.5 centimeter rod being pushed down the page with a speed of 21 centimeters per second in a magnetic field. So what direction do the electrons in the rod move, and what is the induced EMF? So first of all, let's figure out which direction the electrons are going to move. So if the wire is moving down to the page, there's going to be a force that opposes the wire moving up the page. So now we take our palm, face our palm up. Since the magnetic field is going into the page, represented by the X's, our palm is up, our fingers are pointing toward the page or toward the screen, and our thumb is pointing to the right, which means that the current is to the right in this wire. Again, current represents the movement of our positive flow, which means the electrons are moving to the opposite end or to the left. So our electrons in the rod are moving to the left side of the rod. Now to calculate the actual induced EMF. So what we're given in this question, we have our length of the rod, which I'm going to put it into meters, 0.085 meters. We have our velocity is 21 centimeters per second. Divide that by 100 to change your centimeters. So that'll be 0.21 meters per second. We have our B field is 0.32 Teslas. And now we just use our equation. So V equals BLV, 0.32 times 0.085 times 0.21, and that gives us a voltage of 5.7 times 10 to the negative 3 volts. So again, this isn't a voltage of a current moving through the rod continuously, but it's the voltage difference from the electrons moving down to that one end of the rod.